So whenever you write down the electronic configuration of a transition metal ion, the outer shell is lost. It forms an ion, and what you're left with is an incomplete d subshell. Transition metal ions always have incomplete d subshell. So, for example, iron over here has a 3d5. So the d subshell, we talked about the d subshell, that the d subshell has 5 orbitals. And these are the names of those 5 orbitals: dxy, dxc, dyz, x square minus y square, and you had a dz square. These are degenerate orbitals, which means that they have exactly the same energy level, just like the p subshell was the p subshell had degenerate orbitals. They were identical. The only difference was that their orientation was different. The negative charge was on the x-axis, the negative charge was on the y-axis, the negative charge was on the z-axis. Otherwise, the energy level was exactly the same. The orientation was different. The d subshell has a clover leaf shaped orbital, which means that if an electron is over here, the negative charge is spread out in 4 lobes. So negative charge can be felt in all these 4 lobes, which means there's there's no negative charge in the middle of the lobes, but you can feel negative charge on these 4 lobes. So this thing can have 5 different orientations, which is why you have 5 different types of d orbitals, depending on which plane it's lying on. It could be in the YZ plane. So the electron density, or the negative charge of the electron, is found between the z and y axis. It could be between the x and the z axis. It could be between the x and the y axis. So these 3 orbitals were where the electron or the negative charge probability was between the axis. You can find the negative charge between the axis. So there were 3 different orientations for that. There was a 4th one where the electron density was lying right on the x and the y axis. That was x square minus y square. So these 4 all had identical shapes, except that the orientation was different, just like the px, py, and pz. The dyz, dxc, dxy, and dx square minus y square, the orientation of the orbitals was different. The 5th one was totally different. It was more like a p orbital. The dz square orbital, remember, don't think too much about this. This is just a name. It doesn't have any specific meaning. It's just, you just call it a dz square. The electron density was lying on the z-axis, plus it was lying on a donut-shaped area around the nucleus as well. So 5 d orbitals. And I stressed this point that when you talk about the d subshell, all 5 are identical. The electron, in total, you can have 10 electrons. All 5 are separate regions around the nucleus. They're independent, but they're identical. They have exactly the same energy level, only orientation is different. And I highlighted this point that this thing would be very important later on. That dyz, dxc, dxy, the electron density is between the axes, whereas when you talk about the dx square minus y square, or dz square, the electron density lies right on the axis. So this thing, just keep this in mind. We'll talk about that later on. Then we started talking about metal complexes. This is a significant part of what you're going to study in A2. So whenever you have an ionic compound, what happens is a bunch of positive and negative ions all attracted to each other. So copper sulfate is copper is +2, whereas SO4 is -2. So you got copper +2 and you got SO4, which is -2. So this is an ionic crystal, which is a blue crystal. When you mix it in water, the ions dissociate, which means that which basically means that the +2 and the -2 ions, they all get scattered. So this one over here is it's basically copper +2, and this one over here is SO4 -2. So all these ions dissociate in water. And then we talked about the metal ion, which is copper +2 over here. I told you that think of the copper +2 ion roaming around in water. What we discussed last time was that this copper +2 ion is not just going to be floating around in water. What it would do is, all these water molecules are highly polar. I mean, they've got a lone pair, and that lone pair has a very strong, it's got a very strong negative charge. So they've got a lone pair which has a very strong negative charge. So water is a highly polar molecule. So what happens is that they end up forming a dative bond with copper plus 2 ions. A dative bond is where both electrons come from the same atom. So oxygen lone pair gets attracted to the copper plus 2. So the lone pairs of water are getting attracted. They're all getting attracted to copper, which is plus 2. So water molecules from all sides, they get attracted to this copper plus 2. And a dative coordinate bond is formed. So copper ions which are aqueous, from now on, whenever you see copper ions which are aqueous or any metal ion which is aqueous, this is how it's going to look in aqueous state. It's going to form a complex ion, which is that the copper plus 2 over here would be attracted to water molecules from all sides. And the number of water molecules that it can attract, it could vary. The number of water molecules that it can surround itself with can be different. And we'll talk about that in a short while. But this is a complex ion. So copper plus 2 aqueous, next time think of it as this thing. It's a copper ion surrounded by 6 water molecules which are neutral. So this entire thing is a complex ion because copper was plus 2, water was neutral. So the entire thing is has a plus 2 charge. So this thing is called a ligand. A ligand is a species that has lone pairs and can form coordinate bonds with a central metal cation to form a complex. And we wrote down the definition of a metal complex as well, which was it's an ion formed when a central metal cation forms a coordinate bond with ligands. So there are all sorts of complexes that can be formed. You can have all sorts of metal complexes. Coordination number, we talked about the coordination number, that was the number of dative bonds. I think this should have been number. So coordination number is the number of coordinate bonds that a complex can have. So we're going to discuss and we're going to draw a few of the metal complexes. We just drew one of them. So I'm just going to write down or draw the ones, or we can just copy paste most of them. So copper, instead of drawing that, so the ones that you have to remember, copper is one of their favorites. So this is one. So we can, and this one is actually, okay, let's take this as one. Okay, let me draw this. Just 1 second. As we've drawn one of them, I'll just quickly draw that. I'll draw all copper complexes which need to be remembered. So copper plus 2. So let's quickly draw the water one quickly. And there is so you'll be asked to draw a lot of them. So make sure you can show the X, Y, and Z axis in 3-dimensional, and you have this one surrounded by water molecules which are attracted to it. And this one I told you is blue in color. And make sure keep the H away because it's the oxygen lone pairs that are attracted to the copper plus 2. So that's one. We already discussed this one. Let's discuss what is going to happen if you add another ligand. So remember, a ligand is any species that has lone pairs. So what if I add NH3 aqueous to it? So if I add NH3 aqueous to it, what would happen? Now, NH3 is a ligand as well. Ammonia is a ligand because ammonia has these lone pairs. So what these ammonia molecules would do is, like if you keep adding ammonia molecules, and let's say you're adding ammonia aqueous, that means water is still there. So you've got a solution now that's got ammonia as well. So water is still there. You've got this complex, copper ion surrounded by water molecules, but now what would happen is, okay, one by one, the NH3 would approach, and if the NH3 concentration is high enough, then the NH3 molecules would start knocking out the water molecules. So the water molecules might get knocked out. They're going to go away with their lone pairs, and NH3 would start taking its place. Okay, let me draw the lone pair in the correct way. Okay, that's known as ligand exchange. This is exactly what happened. I mean, this was the test for copper ions. You add ammonia aqueous. When you add ammonia aqueous, ammonia molecules, they start surrounding the copper ions, and the water molecules, they start getting knocked out. Okay, is this point clear?
Sir, this only happens when ammonia is in excess.
Let's say you've started adding ammonia. Okay, so one by one, it depends how much ammonia you're adding. If you add more ammonia, the concentration increases, so there's another water molecule that gets knocked out, right?
Okay,
and in its place you get NH3. I said, so you continuously adding ammonia in excess. So here's another a water molecule that gets knocked out. So the water molecules are getting knocked out, and they're getting replaced by ammonia. So this is known as ligand exchange. Just 1 second. All of them. I mean, in theory, it depends on how much NH3 you're adding. So you can, in theory, knock out all of them. So this one is known as ligand exchange. So remember, these molecules with lone pairs, they are your ligands, and they're getting exchanged. One goes away, the other one replaces it. So this one, so remember, it could be, I mean, the number of NH3s is variable. So the number of NH3s that you have in this are variable. So it depends on how much ammonia you're adding. So you could have all 6 getting replaced by ammonia. So this is the complex that's going to be formed, all 6 of them. And ammonia is a neutral molecule, so the whole thing would have a charge of, it will have a charge of +2. If all 6, or you could have, let's say, 4 of them getting knocked out and getting replaced by ammonia. And there would be just 2 water molecules that would be left. Now, water and ammonia are neutral, so the entire thing will have a charge of +2 because copper is +2. So NH3s are variable, just remember that. So they accept this. I mean, they're not very specific. You could have 6 NH3s, you could have 4, you could have 3 and 3. 3 NH3s and 3 water molecules doesn't make a difference. So this one is blue. It's a blue solution. You got to remember the colors. And this one is, I mean, this thing that we have drawn over here, this one is a very deep blue solution. So it's a very, very deep blue solution. So we can, so if you remember the test, I mean, they've, I mean, for example, over here, this image over here on, I mean, we can just copy paste this. Just to give you an idea of color, you must have done, I mean, although you haven't, I mean, most of you haven't done practicals.
Sir, do ligands like attaching to any complex molecule, does it depend on like the type of bonding? Like water has hydrogen bonding, NH3 doesn't, like, does it depend on that? any bonding type?
No, it's not about the intermolecular force. It doesn't depend on the intermolecular force. It depends whether it has lone pairs or not. Okay. So
Okay.
ligand is something that has lone pairs. Because if something has lone pairs, then it will, like this water molecule, then the lone pairs are going to be attracted to the copper ion which is sitting in the middle, or any metal ion. Okay. It could be any metal ion, not just specifically copper. Okay. So for copper, you have to remember the colors. You have to remember what is going on. So I just wanted to show you copper ammonia complex. So the copper ammonia, I mean, this kind of is a good description. This is what happens when you add ammonia. You got a blue solution, now you have a very, very deep blue solution. There are actually 3 steps. It doesn't turn into deep blue immediately. Initially, there's a precipitate formed. If you remember the test of copper ions was you add ammonia, a few drops, you get a pale blue precipitate. You add more of it, more ammonia, you get a deep blue solution. So we're going to discuss this in detail later on. Right now, just remember the complex that's getting formed and remember the color that's getting formed. So that's that's one that you have to remember. Then you have copper with, if I add HCl, concentrated HCl, what's going to happen if I add concentrated HCl to this? Now concentrated HCl. Now HCl is going to have a specific ligand, which is Cl-1, because Cl-1, I mean, HCl is a strong acid, so it's going to dissociate and it's going to have these Cl-1 ligands.
Sir, we have that like deep blue solution complex ion of ammonia. Like if we like add more water into it, like is there a chance that the water molecules will knock out
Exactly.
NH3 molecules?
Exactly. It's a reversible reaction, TK. That's a good point. You can do the opposite as well. TK, remember that. So you can do the exact, all of these are reversible. All ligand exchange reactions are reversible, and we can, I mean, I just wanted to show you the colors at the moment, but you can write this down, that all ligand exchange reactions can go backwards as well. You add water, the reverse happens, and you go back. I mean, this thing turns back into this thing. I said, what about HCl? Now I'm adding HCl. So I said, now over here, the water molecules, they get replaced. I mean, you've got a copper ion in the middle, and you're adding Cl ions, Cl ligands. And remember, I'm adding concentrated HCl. So that means there's a lot of Cl ions. So pretty much all the water molecules, because it's concentrated HCl, all of them, they get replaced by Cl-1. And the Cl-1, they come in and they start surrounding this. They bring in the lone pairs. The water molecules have been knocked out. And because it's concentrated, so all of them are knocked out. If it had been dilute, then some of them would have been knocked out, not all of them. I say, anyways, so you got this thing, which is instead of, now the shape is different actually. It's just 4 of them. When you have 6, the shape is octahedral, which means all ligands are lying on the axis. But with Cl-1, you've got just 4 of them. And there's a reason why only 4 are surrounding the copper ions. The reason is that Cl-1 is a bigger atom. I mean, it's got an AR of 35 or 37. Water has an MR of just 18. So water has almost half the size. I mean, water is very small. Cl-1 is bigger in size. So think of it, there's a spatial problem over here, because you can't, if you have big things around it, you can't fit a lot of them. Like if I just draw these random circles, let's assume that Cl is kind of big in size. So if it's bigger in size, you run out of space around it. So you can't fit 6 of them around it. So just remember Cl-1 is bigger in size and it usually forms a tetrahedral complex. Only 4 of them are able to actually fit around the copper 2+ ion. Is this point clear?
Yes. If I wrote like instead of you wrote just Cl, if I wrote HCl, would it be wrong?
कहाँ पे यहाँ पे HCl?
Yes, yes.
नहीं,
Yes,
HCl
HCl.
HCl is not a ligand. It's usually not a ligand because HCl ionizes always. It's a strong acid. So in solution,
Gotcha. Yes, yes, yes.
okay, so in solution you don't usually have HCl. You have H+1 and you have Cl-1 separately. So anyway, so remember this. You got to remember this, and remember once a complex is formed, the charges. I mean, you don't write individual charges on the atoms because now the charges are on the whole thing. So what is the total charge of this entire complex now?
-2.
Okay, so it's -1, -1, +2, -1, -1. So the total charge is -2. That's the total charge. It's so rub off the charges on the individual atoms or ions because they're all together now. So the charge would be on the entire thing now. So this one is CuCl4. And it's got a charge of -2. That's the charge that it's going to have. And the color for this is going to be greenish yellow. So this one is greenish yellow. That's with Cl-1. So you've got to remember this one as well. And if we do have, I'll just copy paste it so we get good notes. Just a second. Copper. So it's this one. I'll just for reference, I'll just copy this image. So CuCl2- is greenish yellow. And also remember, it's a tetrahedral complex. You have to remember these things because remember, all complexes are different from all other complexes. It depends. I mean, you can't predict whether it's going to be tetrahedral or octahedral because it all depends on the ratio of the size of the ions. Like how many can you fit around it? So it varies from different ion to different ion, and from different ligand to different ligand. So you can't. There is no simple formula where you could figure out whether it's going to be 6 or whether it's going to be 4. So most of the time you just have to remember them. So you have to remember them for copper. You have to remember them for cobalt. I mean, these two you got to remember. So I'll just add to this that this is a tetrahedral complex because it's got a tetrahedral shape. And these other ones are octahedral complexes, which is obvious. It's 6 bonds. The shape is octahedral. NH3 is almost the same size as H2O. Like NH3 is 17 and H2O is 18, I think. So the MR is kind of almost the same. So you can kind of predict that NH3 and H2O will pretty much do the same thing. So, but remember, your thing is that you just have to remember it for copper. I'll add one more to this. There's one more complex that has to be, you got to remember for copper. And also for cobalt as well. So one more that you have to remember is with OH ions. What if I add OH ions? So let me draw an arrow. Okay, so what's now? Let's say I add OH ions. Now with OH ions, what you usually get is, again, you got a copper in the middle. So you got copper +2 in the middle. And OH almost has the same size. So it's going to be octahedral as well. So one at the top, one on the bottom, one on the x-axis, one on the. So you got something on the x-axis. Then on the y-axis. Now for OH ions, what happens is that for OH ions, you have to be very specific. For OH ions, let's say you started adding NaOH. I'm just going to add. Just give me 1 second. I've lost the board. Just 1 second. Chale, this one. With NaOH. TK, my point is there. So if I start adding NaOH aqueous, then obviously I've got OH ions coming in. So my water molecules, so previously I had all these water molecules, and those water molecules are going to be, those water molecules would slowly get knocked out and they would be replaced by OH ions. Okay, so let's say initially they are just water molecules with lone pairs. And slowly those water molecules, they get knocked out and they get replaced by these incoming OH ions coming from NaOH. So OH ion comes in, this water molecule gets knocked out, gets replaced by OH -1. And the water, so this is formed. Now the thing with this one, with this specific complex, so the thing with this specific complex is, the thing with this specific complex is only 2 OH ions are able to actually replace the water molecules. So unlike what's happening with NH3, with NH3, I told you that there could be any amount of NH3s. You can keep on substituting the water molecules with NH3 molecules. But the thing with OH ions is you got a limit. You can't exceed 2 OH ions. So does anyone have any idea why only 2 OH ions? Why not more? Why can't the other 4 water molecules be replaced? Just a random guess, anyone?
Because NaOH is in aqueous and not concentrated.
Let's say even if it's concentrated, like you add more NaOH to it, even then, you'll be stuck with just 2 OH ions. You can't. It would be very hard for you to actually remove the other water molecules, and I'll explain the reason for that. The reason for that is that when you have 2 OH ions, before you had 2 OH ions, this thing had just 1 second. So वापस 1 second में चले जाए. So this one. I forgot to write the charge on this thing. This entire thing had a charge of. It had a charge of +2. Now focus on the overall charge on this thing. So right now with 6 water molecules, this entire thing has a charge of. It's got a charge of +2. So at the moment, it's got a charge of +2. the OH ligand is negatively charged. So that means the OH minus 1 is going to be attracted to it. But once you got two OH ions in, the problem would be, what's the overall charge on the entire thing now? Once two OH ions have substituted.
0.
Okay, so that's 0. So you got no charge now. So that means the OH ions would not really be interested in replacing any of the ligands. They wouldn't be attracted to it. And let's assume that for Cl you're using exactly for so the thing with Cl is that Cl, it depends on the lone pair density as well. I mean, Cl minus 1, you're using a very concentrated Cl. So that's one of the reasons why you're doing that. You're using a very concentrated HCl. Okay, over here, this would happen. So I'm just explaining that if you add NOH, this would happen here as well. But the thing would be that once you get the third OH ion in, now you've got a negative charge. Okay, now you've got a negative charge. Now the problem is that the OH ions are going to be repelled. So the thing is, I mean, we can assume that this is dilute NaOH we are talking about. Not, unlike this one, not concentrated HCl. That could be one of the reasons you're using concentrated HCl over here. Let's simply code this as, or use, or just state this as dilute NaOH. This one. So this one. Now with OH ions, the third one, it becomes negatively charged, and all the OH ions are going to get repelled. And there's actually another reason why the third OH ion, it's harder to actually get the third OH ion in. And that is, let's put this as water. Again, you've got two OH ions in. What happens is that this is now copper hydroxide, basically, with 4 water molecules. Now, copper hydroxide is insoluble. I mean, it's not very, very soluble. So it's an insoluble precipitate. So it's going to leave the solution and form a precipitate. And it's a pale blue precipitate. So I suspect it's got something to do with the solubility as well. That copper chloride, no matter what the copper chloride is, chlorides are mostly soluble. Chlorides are very soluble, except for silver and lead. Most chlorides are pretty soluble. So they remain part of the solution, which is why the Cl minus 1, they keep on coming in. But when it comes to copper hydroxide, as soon as copper hydroxide is formed, it's an insoluble precipitate, and it just leaves the solution and ends up forming a precipitate. What if we use concentrated NaOH? My assumption is that if you use concentrated NaOH, getting the third OH ion in would still be difficult, because the precipitate would just leave the solution. It would no longer be part of the solution. It would just form a precipitate, a crystal, and it would just leave the aqueous solution. So that's why probably the third OH ion, it's harder to actually get the third OH ion in, because it's probably going to form an ionic lattice. And ionic lattices are tightly packed. They're close together. All the particles, the copper ions and the OH ions, would be all tightly held together. So once the ionic lattice is formed, and it's an insoluble ionic lattice, you probably can't really get or sort of add more OH ions now into the crystal. Do you get the point?
And sir, what if we used like dilute HCl instead of concentrated? Would that affect? formation of
Yeah,
CL lines.
you'll get fewer CL lines. Okay. So the thing is, now remember this, ligand exchange is not like, it's not like 100%, it's something is going to happen. Like it's not, even if you add concentrate HCl, I mean, you're not always sure that there would be 4 Cl lines. I mean, it's not a given that there would be 4 Cl lines. Same as this one, like if you add NH3, it's not a given that all of them are going to get substituted. So ligand exchange, you can't say for certainty what type of complex would be formed, but you can only predict that this is something that would happen. Now for A2, you have to remember the colors of these specific complexes for copper. You have to remember copper with 6 water molecules. You got to remember that. Copper with, if you add NH3 to it, it becomes deep blue in color. Okay, you have to remember this color. You got to remember if you add concentrate HCl, the Cl lines are going to form a tetrahedral complex, which is a greenish yellow solution. And the last one is if you add NaOH, you eventually get a precipitate because copper hydroxide is insoluble, and you get a pale blue precipitate. So you got to remember all these colors for copper, and cobalt has exactly the same complexes. So you got to remember those as well. So I'll just copy cobalt's colors, and they're exactly the same. They're exactly the same colors. Just a second, if we can. Sorry, let's just copy. So cobalt is going to have exactly the same complex, just remove copper and replace it with cobalt. The colors would all be different. So I'll just so this is a cobalt. I'll write the colors for cobalt. So cobalt, if it's with 6 water molecules, and let me just add on top cobalt complexes. So the first one is pink. I mean, if you know that cobalt, remember it was used as a test for water as well. So cobalt, when you add water to it, it turns pink, and this is the pink color that you get. Cobalt with water and OH ion, that's an insoluble precipitate, and it's green. It's a green precipitate. You add ammonia to it. Cobalt with ammonia, that's a brown solution. With 6 NH3s, I mean, the number of NH3s can vary. And the last one you don't need to know. I mean, we can just cut that out. And there's actually one missing, and that is cobalt with Cl. So there's one missing, and we can add that. So this one is cobalt with 4 Cls, tetrahedral complex. It's 2 minus, and this one is a blue solution. So this one over here is a blue solution. So you need to remember the colors of cobalt complexes as well. TK, is this clear?
Yes, sir.
And specifically copper and TK. What I'll do is, I mean, it's on this board. Just a second. I'll send the notes over here. ठीक है, notes चले गए. What you can simply do is if you open this over here, there's a save as option. You can save it as a PDF. I drew के ऊपर ना this. I did do this. Just a second. So you can save it as a PDF. It will be saved as a PDF. ठीक है, वो आ गया PDF. Or in image, or you can simply copy it down from all the notes. Previous ones are also written over here. Okay. So just remember, you don't have to remember all the complexes. You just have to remember a few of them. Copper and cobalt. That's it. Okay. So we'll continue from this point onwards in the next class. Okay. Okay. Sure.
Allah Hafiz, sir.
Okay. Take care. Allah Hafiz.